All right. So I forgot to turn on the recording earlier, so I'm going to go over the notes in this video about the 10.1 parametric curves that we talked about in class today. So here we go. First off, a parametric curve involves x and y related to a third variable, and that third variable is usually t. So parametrics will take the form typically of x equals some function f of t and y equals some function g of t. So for example here, we'll start with this one. X is t squared minus 4 and y is t over 2 from -2 to 3 for t. So if I was going to draw this using these parametric equations, if I was going to draw what the graph of this would look like, I would probably start off by making a table that looks something like this. We have t, x, and y, and then we're going to go through and put down the values of, in the t column, -2, -1, 0, 1, 2, and 3, to go from -2 to 3. And then we'll plug each of those values of t into the x and y equations to get our x and y coordinates at that time t. So here's that. We plugged in -2 and got 0 and -1. Plugged in -1 for t and got -3 here and -1/2 here. Plugged in 0, 1, 2, and 3, and these are all of the coordinates that we got. So when we go to graph this, we're basically graphing all of these coordinates and then knowing that we start here and we end here. So my graph ends up looking something like this. My initial point is at 0, -1, and my ending point is at 5, 3/2. So starting here, my next point is here, then there, there, and there. So this, oftentimes when we see parametric equations graphed, it'll have arrows indicating the direction of travel. So we'll see something like this. Also, something interesting to note, each of these dots, the time distance between these dots is the same. So from here to here is the same amount of time as it takes to go from here to here. So that tells us then that that if there was like a particle moving along here, it would be going much faster in this section to cover the same amount of distance in the same amount of time as it takes to go from here to here and cover this much shorter distance. And that's something we'll get into a little bit more even when we talk more about parametric calculus and stuff like that. Since today is really just an introduction to how parametrics work and not so much the calculus of the parametrics. But there is also something in our calculator that we can do to graph this as well. So I wanted to show that real quick here. There's a mode in your calculator called parametric mode. So if I hit mode, you can see on mine it's already highlighted. If you go down here to where it probably has function highlighted for your calculator right now, if you slide over to parametric and hit enter, something that will happen when you hit y equals, also make sure your calculator is in radian mode, otherwise things will look weird later on when you start graphing circles. When you hit y equals, all of a sudden you have an option for x and for y, and your variable, when you hit the variable button, ends up being t. So it allows you to graph things, graph parametrics. So if you type in the function that we started with, t squared minus 4 for x and t over 2 for y, and then you go to the window, and we know our minimum value of t was -2, the max was 3, and the steps we were taking for time were size 1. And then I just played with the x min and max and the y min and max so that our function ends up being in view. So that's the setup I put, and then you hit graph. And notice, 1, it graphs it really quickly, but 2, it graphs it a little bit jaggedly, kind of like ours. You can definitely see where it started and where it ended, and you can see the different points along the way that it hit. If you want it to, one, slow down a little bit, and two, graph a more smooth curve, you can also change your window and the step size for time. If I change it to 0.1 instead, it graphs it a little bit more slowly and a little bit more smoothly. You do the same thing again, change it to 0.01 if you'd like, and it takes even more time graphing it and even more smoothly. Notice though how it's almost imperceptible, but it does speed up as it's going through longer sections in shorter periods of time. And then it slows down when it gets to this part where it's able to travel slower to cover a shorter distance in the same amount of time that it took to go the longer distance. Anyway, that's something that you can also do. If you hit table, it'll show you time, X and Y, so you can take a look at those as well. So yeah, handy things we can do with our calculators for parametrics. Another thing we want to be able to do is do something called eliminating the parameter. So this will give you rectangular coordinates instead, the sort that we're used to seeing, the type of function that we're used to working with and graphing and things like that. So in order to eliminate the parameter, what you need to do is take your x, or for in this particular case, and what will work in a lot of cases, is take your x value, your x function, and solve for t, and then plug it into the y for t. So for this particular one, solving for t over here gives you add 4 to both sides, take the square root, remember it's plus or minus square root of x plus 4. Then, since y is t over 2, you can just plug in this instead of t, and we get y equals plus or minus root x plus 4 over 2. All right, and if you were to stick this into a graphing calculator when it's in function mode instead of parametric mode, it will graph the path looking like this. There are some advantages to working with parametrics, though, as opposed to rectangular coordinates. Parametrics show path, direction, and speed. Rectangular only shows the path. So rectangular will only show basically a sideways parabola here. But the parametric shows what direction this thing is going. So that's why it's really useful for things like problems with a particle in motion, finding speed, velocity, acceleration, all those things at a given time, where rectangular is not as helpful in that area. So anyway, that's a basic introduction to parametrics. Now let's dive a little bit deeper. Let's take a look at circles. Some interesting things that happen with circles here. So with our next example, we're going to be dealing with the function in parametrics x equals cosine of t, y equals sine of t. So this particular function might look kind of familiar because you are hopefully familiar with the unit circle. In the unit circle, x is cosine and sine is y. So same kind of thing happens here. If I'm going to eliminate the parameter for this one, when you're involving trig functions, usually it's a good idea to use trig identities, particularly in this case where we have cosine and sine. Knowing that sine squared plus cosine squared equals 1 is going to help us out a lot, because then all of a sudden, well, cosine squared is the same thing as x squared, and sine squared is the same thing as y squared. So I can substitute those things in. Actually, I did this, a little bit backwards, but that's okay. If I was directly substituting and showing my work a little bit nicer than this, I would have x squared here and y squared here. But anyway, this is the standard format for the equation of a circle, right? Centered at 0, 0 with a radius of 1. Or if you wanted to solve it for y, you'd have plus or minus root of 1 minus x squared, which is more of what you would plug into your calculator if you wanted to plug in the equation in rectangular coordinates anyway. And it would yield a circle. Or it actually looks a little bit more like an oval depending on how you space it, because the calculator screen is rectangular. But anyway, it's supposed to be a circle. Okay, so what if we were to generalize this a little bit? What if we wanted the parametric for any circle with a radius of r and centered at hk? Well, if we're just changing up the radius, then this is how it would work out. R cosine t and r sine t. Sorry about that, one sec. That was my dog, not some ghost I'm letting in and out of the room. Anyway, if hk is 0, 0, if it's centered at the origin, we're just messing with the radius. This is what we get. But if we want to move it around, h is the coordinate that corresponds with the x value of the center. K is the y value of the center. So h is going to go with the x coordinate. K is going to go with the y coordinate. So if I would like it to start someplace besides 0, 0, that means I'm going to need to add this value to this. So we get x is h plus r cosine t. Y is k plus r sine t. So that's another thing that we should know, dealing with parametrics and equations that look circular. All right, this next bit is going to look a little bit crazy, and it comes from number 26 in your textbook. So the pictures in your textbook are a little bit nicer than the ones that I can draw. So for a lot of things with parametrics, we're going to be looking at pictures that are computer generated and not Miss Lindell generated. I did my best to draw these ones, and I will talk through this example. So yeah, let's get to it. So starting off, looking at this massive colorful picture of things, what this problem started out looking like was just number 26 right here. It gives you an x and a y, and it says to use the graphs of x and y to sketch a parametric curve, indicating with arrows the direction in which the curve is traced as t increases. So what we want to do is take these two things and basically do what we were doing with that other, with our first example, putting it into rectangular coordinates, but this time I don't have the actual function f of t and g of t for x and y that I can use to plug in actual values. So for this, we're going to have to estimate a little bit and kind of deduce the behavior of our function based on the behavior of these curves. And what's going to take some getting used to is looking at this as an x-axis, because the x-axis is usually here. But this is time, or t, on both of these. So it does take a little bit of getting used to. We're going to talk about things like as t increases, what's going on with x, as and what's going on with y, and trying to combine those things to tell us what the function is going to look like. So as we can see here, I've already done a lot on this. So when time is 0, notice how when t is 0, x is 0, y is 1. These are definite values that we can figure out here. In fact, anytime that x is 0, I'm going to make a note of it down here. So that means when time is 0, when time is 1, and when time is -1. Those are all places where x is 0. So that's a good place to start. There's only one place where there are two places where y is 0, but it's encompassed in the two places, or in two of the places where x is 0. So first, when time is 0, x is 0 and y is 1, because that's when time is 0 right there. So we know we're going to pass through the point 0, 1, and we know we're going to do it when time is 0. When time is 1, x is 0 and y is also 0. When time is -1, x is 0 and y is 0 as well. So we know we're going to pass through the origin twice, both at time is -1, and time is +1. So now we want to start kind of just looking at the graph of x from left to right, looking at the graph of y from left to right, and figuring out from that behavior what's going on with our coordinates. So starting off when time is less than -1. So that would be this branch of the graph for x and this branch of the graph for y. We know that x is positive since it's all above the t-axis, and it's decreasing towards 0. We know that y is negative and increasing towards 0. Because at some point, when time is -1, we're going to get to 0, 0. So that means my x value starting the function is positive. My y values are negative. We're going to be increasing up to 0, 0 here. So this is that branch where time is less than -1. This is when we get to time is equal to -1. Next, we've got this spot from -1 to 0. -1 to 0 for time. In this case, x is negative, but it decreases and then it turns around and increases. My y values are positive and increasing. That means that this part of the function, my y values are all going to be positive, my x values are all going to be negative, and they're going to be decreasing at first and then turn around and increase. And then basically the function is going to do the opposite. The behavior over here, x values are positive and they increase and then they decrease. Here my y values are positive and they're decreasing the whole time. So that's where we see this. And then lastly, when time is greater than 1, my x values are negative and decreasing. My y values are also negative and decreasing. So we're going to negative and decrease away. So that is how we take two parametric curves and turn it into rectangular coordinates, showing our parametric curve with the arrows indicating the direction that we're traveling. Okay, and there's a problem on the homework number 25 that is a lot like this. So same process. Okay, last thing we talked about was from number 28 in your book, which also has a lot better pictures than I can draw. It's a matching question. It says to match the parametric equations with the graphs labeled Roman numeral 1 through 6. And give reasons for your choices. Don't just use a graphing calculator. So we're going to look at part B for that one. So number 28, part B, looks like this. We've got x of t is t squared minus 2t. Y of t is the square root of t. And so we're trying to narrow it down between these 6 options down here. So this is our function for b, t squared minus 2t, and the square root of t. And I want to narrow it down between these 6, figure out which one that represents that function. So the first thing that I'm going to look at is there anything positive, negative-wise that I can rule in or out for my x and y values? And the first thing I notice is the square root of t is always going to be greater than or equal to 0. So that means that y of t is always going to be greater than or equal to 0, so I'm not going to have any negative y values, which means I can automatically rule out a lot of them. These are the ones I'm ruling in. 1, maybe 4, and 5. Because on 1, we clearly only have positive y values. On number 4, I'm not entirely sure if this dips below the x-axis or not. So 4 is a maybe, and then 5 also doesn't have any negative y values. All these other ones have negative y values, so we can rule those out automatically. The next thing I want to do is figure out where x and y are equal to 0. What values of t does that happen for? Because looking at these 3 now that I've kind of narrowed it down to, for this one, it doesn't look like x is ever 0. So that's kind of something to be paying attention to. For this one, it looks like there is one place where x is 0, and for this one, it looks like there are two places where x is 0, here and here. So since that's the case, let's figure out when is x 0. So I'm going to set 0 equal to t squared minus 2t. And then we can factor this thing, and we get t times t minus 2, and we got all blurry for a second. There we go. And so then we get t is 0 or 2, since we set each of these pieces individually equal to 0. So that gives us two places where x is 0. And so if I plug these times in for y, we get 0, 0, and we get 0 root 2. So since it's two different places also, two different values of y for which x is 0, we can see pretty clearly then that it must be number 1 that matches with that function. Okay, so those are just some strategies you can use to kind of narrow down if you're trying to match parametric curves with their function without using a calculator. That's a way that you can do it. Looking for places where x is 0, places where y is 0, things that you can tell from the function about x and y. And that's pretty much everything that we covered in class today. We also talked a little bit about just, what the homework problems are and everything. So the homework for today is 5 through 18 and 25 on 10.1. All right. That's all we've got for today. Have a good one.